And we're on to the last presentation in this Engineering with Julia mini symposium. Thanks to everyone for hanging out. We have Ronan, right? It's going to be.
Let's see. Okay.
Yeah, you're pretty close. All right, great. Obrigado.
Okay.
And let's get going. Satellite. Yeah, some cool stuff. Satellites with Julia, right?
Okay. Good afternoon, everyone. I'm very glad to be here at JuliaCon one more time. Today I'll talk about how we are using Julia to turn gains in our next satellite. I'm not going to present a new package or a new technology or a new feature. I'm going to present how we are taking those packages that we now have in the Julia ecosystem and integrating them to create a very, very good application. For those who do not know me, my name is Ronan. I work with the National Institute for Space Research in Brazil, where I am the mission architect of the satellites Amazonia 1 and Amazonia 1B, and also the technical lead of the attitude and orbit control subsystems. In the Julia community, I'm the developer of some packages like satellite to box, reference frame rotations, pre-tables, terminal pages, and some others. But just to recap, for those who missed my talk 2 years ago, Amazonia 1 is the first remote sensing satellite that was fully designed and integrated in Brazil. It's based on the Brazilian multi-mission platform, was successfully launched on February 2021. And Julia was a key technology during the development of the attitude and control subsystems. This was a project that allowed me to create satellite to box and some other things. Okay. Since this was our very first project, we have to buy a lot of equipment with spares, because if you are integrating, and let's say it's our first project, right, based on the multi-mission platform, and something goes wrong, then we can use the spare part without have to waiting for the manufacturing or something like that, which will lead to many delays. But now we have, everything went fine. We did not use those spare equipment. So we have a lot of spare equipment, and we are taking those and building another mission, which we are calling Amazonia 1B. The attitude and orbit control subsystem, which I call it AOCS from now, it's exactly the same, but the payloads are different. Now we are using a higher resolution camera called MUX camera and a GNSS-R receiver. So this is a picture of the satellite being integrated in our laboratory in Brazil. But before I'm talking about what we did, I need to get some, provide some background about what is attitude control. Attitude and not altitude is how an object is in space. For example, my cell phone here has one attitude. If I change it, so now it has another attitude. This is attitude, how something is positioned in a 3D world. But what is attitude control? To show this, I want to play this footage of Amazonia 1 right after the orbit injection. So this was recorded by the launcher. And the satellite is being injected on orbit. It will open the solar panels. And the system will start to change its orientation so that the solar panels here points towards the sun. This is attitude control. You change the orientation of the satellite to do what it has to do. In this mode, we need to point the solar panels towards the sun. During the routine mode, it needs to point the camera towards the Earth so it gets the image. But how do we control the attitude? In the multi-mission platform, actually, in most of the satellites that use the same design use a very similar diagram as I'm showing here. We have a control reference, where I want to point, and we have a attitude estimation. We compared both, and then we got an error, an attitude error. This error we send to a controller, which in this case is a PD controller, proportional derivative, that generates a torque signal that we send to the reaction wheels that change the satellite attitude. This attitude change is measured by our sensors, in this case, star trackers and gyros. The information is then sent to an attitude estimator, and the loop continues. So pretty simple how we control the attitude here. But the question is, okay, we have those things called reaction wheels. How reaction wheels change the attitude of the satellite? In this picture here, we can show the reaction wheels in the multi-mission platform, right? So are those wheels here. It happens by the conservation of angular momentum. If you spin something in the satellite, we only have internal torques, so the angular momentum must be conserved. Hence, if you spin something in one direction, the rest of the body will spin on the other direction to conserve the angular momentum. This is a very nice video that a student at INPE did, recorded, called Mateus. This is, let's say, something like a satellite mock-up. It's spinning around one axis, and on top of here, there is a motor with a mass attached to it. Oh, sorry. So it's spin, and the Mateus will turn on the control eventually, and you see that the device will more or less stop here. So what it did, it starts to spin that mass to incorporate the angular velocity. So it's very simple, right? If you control those, the velocity of those wheels, we can control the attitude of the satellite. This is how we do. Okay, moving forward. Among many things you have to do to design an attitude control subsystem, one of the most important steps is to obtain a good set of parameters, the control gains and the filter parameters. In Amazonia 1, we use a very known software to do this, using what normally control engineers do. We assume a linear dynamics. We assume that everything is linear. If, under this assumption, we have a very large theoretical background to work with, and we select the gains under this assumption, take those gains, put on a highly accurate simulator, check if everything is okay. If it is okay, fine. If it's not, we repeat. So just to show, this is the design, considering that everything is linear and so on. When we take, so sorry for the labels in Portuguese here. This is the pointing error. This is the time. We are applying a step signal here. So and each curve is the pointing error. It should follow that step curve here. So when and each curve here is one project, a set of different gains. When we took those gains and put on our simulator, the result was completely off. Why? Because there are many non-linearities in the systems. The most impactful was, of course, the reaction wheel torque and angular momentum saturation. Since it is a motor, we have the maximum torque it can output, and if it starts to spin too fast, it cannot spin anymore. So it will not provide torque anymore. So we have those non-linearities that are very, very impactful. That's why we see those differences here. So the process was like a trial and error. We try try a set of gains that complies with our requirements, with stability requirements. We go to the simulator, if it's good, okay, and that's why we have a lot of projects here. But in the end, we managed to do things correctly. That's why we are seeing those kind of pictures. This is a picture from the south of Florida, I think, took by Amazonia 1. You can see we have a very sharp image. Let's say the satellite is 700 kilometers above the Earth, and we are taking a picture in a way that we can see, I don't know if oh yes, we can see a road here, we can see a boat here. So the satellite is very stable, okay? So we know that the gains are correct. But INPE is a research institute. One of the things we need to do is to improve things, find better ways to do our process, and so on. So I decided to see if we can use Julia ecosystem to improve the way we are turning the control gains for our new mission. Because even though the system, the OCS, is exactly the same, the satellite is not. So we have a different inertia. We have to obtain new gains for this new mission. So we developed an application integrating those tools: Modeling Toolkit, Control Systems, Mach-E, and Satellite to Box. In Modeling Toolkit, we obtained a simplified model of the satellite. We can design the gains for each axis individually. And we decided to try to make the simple model we can without sacrificing the accuracy. Because since we want to make a kind of real-time project, I will show what I meant by real-time project, we would like that it can run fast. Unfortunately, I cannot show to you the entire model, what we did, but I'll try to make a simple version here so you understand what we did. The first thing is to remove everything we don't need. And the sensor dynamics is not necessary to obtain the control gain, so we just remove all those sensor dynamics here. And using Modeling Toolkit was a very nice experience. It was the first time that I used Modeling Toolkit for something in the project. Because for a control engineer perspective, you just need to take those blocks, find the inputs and outputs, what the parameters are important, and then connect everything. It's very simple, very easy. So, for example, for the proportional and derivative controller here, the input is the proportional signal, the derivative signal, and the output is a function of those two inputs multiplied by the parameters here. The proportional and derivative gains are declared here as parameters because I want to chain them so that we see the modification in the output. The reaction wheels, okay, this is a very, very, very simple model. I just take a input torque and create here an output torque, which is the input torque clamped between two limits. The model we use is way more complicated, but this is what I cannot show you, unfortunately. But it was much more complicated, but you understand the idea here. For the attitude dynamics, we receive the net torque from the reaction wheel, and the output is just a state variable. So we have the acceleration, the angular velocity, the position, which is the attitude here in one dimension, right? And when we write those equations here for these dynamics. The inertia here must be a parameter because since we are doing it by each axis has its own inertia, so we need to change this. And finally, we need to take those blocks and connect everything using another model. We call it here one-axis satellite simulation, something like that. And we have those three components: the PD controller, the rigid body dynamics, the reaction wheel model, and then we just write the equations related to this diagram here. For example, the input to the controller is the error signal between the reference and our current attitude value. So we have this for the position and this for the velocity. The output of the controller is the input for the reaction wheel. So the input for the input for the reaction wheel is the output for the PD control, and so on. So it was very easy. Modeling Toolkit, this kind of design, it's very good. Finally, you build the system here. By the way, I'm using here the version 9 of Modeling Toolkit. I know there is version 10 with a lot of improvements, but I didn't have time to update. But obtaining this system here, you can use the differential equations to integrate everything. But if you do something like this, you have something running in the terminal outputting numbers. It's not fine. Of course, we can have some kind of auto-tuner and so on, but I would like to make something more interesting, more easy to see, to understand. So I decided to build a graphical user interface. I'm not good at building graphical user interface, but thanks God we have Maki, which was amazing. I could do this very easily. I want to show you what we have. Let me run here. The first thing, I need to select the axis that I want to analyze. Let's see, the z-axis. I also need to select the solar panel position because in this model, our solar panel is quite big, so it has a little bit of flexibility, and this can perturb the attitude, so we need to consider it here. Let's use 0 degrees. Okay, so you have this GUI here. I don't know, oh, you can see. On the top part here, we have the classical control information, which we are obtaining from the control system diagram, the board diagram. We look to this information to check if our project is stable enough, given our requirement. On the bottom part here, we have the time response. This is obtained by taking that modeling toolkit model, running the differential equation solver, and obtaining the answer. We have some information here to make my life easier. And then we have the sliders to change the parameters. At this point, I was very afraid because if every time I change this slider, I will update the model, send to the differential equations, obtain the result, send to Maki to update the plot. If it takes like 40 seconds, 1 minute, it will be unusable, right? But I was really amazed when I saw this. It's in real time. So it was so easy that I do not even consider to use an auto-tuner because I can use our expertise just to obtain good gains. For example, here, I do not want to saturate too much here. I do not want some overshoot here. Okay, the gains are tuned here. I press save figure, since it's a Maki window. The figure got saved here, and I can copy it to my report because I have to report everything that I do. And everything works fine. To use that, remember that I said when I was using the first approach, the result we obtained here was completely different from the simulator because this saturation here. Normally, we do not want to saturate the actuators. But if we do not saturate the actuators here, like this, the system is very slow because the reaction wheels do not have a lot of power. The torque is in millinewton meters. So it's not a possibility here. That's why the non-linearities here must be considered during this phase. Okay, I'm running out of time. Fine, but this was the project. What about the satellite? So we designed, this was the real design for one axis of the Amazonian 1B. We took this design, we implemented it in the computer, and we performed we call it the satellite in the loop simulation. We have the satellite, we have this equipment that simulates the orbital dynamics and so on, and everything was working as the satellite would work on orbit. And this was the result. It's not the same, of course, because it's almost impossible to replicate these initial conditions. But we can see this part here. Here, the system in the design tool goes from 0 to 30 degrees, which is the same angle difference between here and here. The time span here is the same time span here. We can see that, of course, here we have initial velocity that we do not have here, so this is a little bit faster. But the satellite is pointing to the reference without overshoot in a very similar time. So the design was spot on. And it allowed me to obtain the gains in just one try. I obtained the gains, I sent to the computer, we tested, and everything was fine. So our conclusions, we developed this tool to turn the Amazonian 1 control gains. This shows how amazing the Julia ecosystem is right now, so that you can take those completely different packages and integrate them in very nice applications. We have 4 modes in the satellite, 3 axes per mode, 2 parameters per axis, and everything was obtained in less than a day after I coded this application. And the results with the satellite in the loop simulation was spot on. It was very interesting to see. I sent to the Julia Space, how can I, here. I sent to the Julia Space organization in GitHub this repository called Satellite Attitude Control Design, which is the model I showed here, the simplified model, not the one we use. Unfortunately, I cannot do that. But the simplified version with the Mackie GUI and everything, how we connect everything, the observables and so on, so you can check out if you like. Okay, that's what I want to talk. Thank you very much. I'm open to questions.
Thank you, Ronan. That was great. Are there any questions? Yeah, I'll come up, bring the mic.
Yes, thank you. How would you compare your experience of using the well-known commercial control system tuning software to Modeling Toolkit? What are the areas of improvement for Modeling Toolkit? And have you started looking into Dyad? And will that be useful? Thank you.
Yes, it will be very useful. I like programming, so I'm very happy to write code. But a lot of people in my institute do not like it. It's like a graphical user interface to plug things in. And Dyad is reaching this point. I saw a lot of talks about Dyad, and it's very good. I'm really looking forward to analyze it and how we can add those kind of, because this was a very successful applications of Julia and Modeling Toolkit in analyzing satellite dynamics. So now it's time to explore the same things in other areas, like thermal control, or add more information, more data here to increase the accuracy, something like that.
All right, any other questions?
Yeah, I was just wondering why a GUI must why a GUI is the tool of choice for tuning some parameters. Mostly I see GUIs used as exploring some parameter space, trying to understand the problem of choice and so on. But I rarely see that some parameters are picked using that way, right? Because I don't know, I would expect some optimization function running over the space and picking whatever is the best value. So I was just interested in why it's done like that.
Actually, the idea to create this GUI to see the gains was just a proof of concept. And it became so easier to turn the game that we just use it. But it's not that easy because we can have some kind of cost functions, but we have some stability requirements. Yes, we can obtain this, but it's not necessary. We saw this, it worked beautifully, it fits within our design constraints, so why complicate?
All right, any other, okay, coming back. All right, here we go. Nice,
I like it. Thank you. Regarding visualizations, what are the next features you would want to see in the Mackie ecosystem to take full advantage of Satellite Toolbox and your other tools? And I'll also ask the opposite question. Are there additional features needed in Satellite Toolbox to take better advantage of Mackie?
Regarding the first part, I cannot answer because I do not use too much Mach-E. I use Mach-E a lot, but not all the features it has, so I cannot answer. For the second question, in the satellite to box, not in the satellite to box, but there is another package called satellite analysis, which I am using Mach-E a lot through extensions. So there are a lot of things to do. For example, computing access analysis. We have a plot, we have a mission, we have a sensor. How many times a day a satellite will pass through that point? How many times it will take to see this point twice? So this is something I will do. I did a little example, proof of concept. It works fine using another package called meshes together with satellite to box and Mach-E. So in the next months, I'm looking forward to make more integrations between GeoMach-E and satellite analysis.
Hi, hello, very nice talk, very inspiring, I would say. In that regard, I'm wondering, like, if using Julia, for instance, with your Brazilian team, help in somehow to either expedite the process, like accelerate it, or also, I don't know, create some kind of community or enthusiasm, or, you know, this is a great tool, it's kind of free, open source, like, is it, people were happy about it, like, people change very easily. Can you comment on that?
Yes. I was a very early adopter of Julia. The first version of Julia I used was 0.2 because I was very upset of having to rewrite my entire PhD thesis in C due to a very slow computation. So I learned about this language that's supposed to solve my problem, and I start to write a lot of functions related to satellite that does not exist. Today, we have such nice environment that Julia became very, I would say, popular at INPE. So we are using Julia to analyze the telemetry of the satellite. We are using Julia to design the LCS. We are using Julia to design our next version of the embedded software. And the way everything is connecting really helped us to make all those tasks more efficient.
All right, well, I think this wraps up the Engineering with Julia mini symposium. So thanks to all the speakers, including Ronan, and all of the participants.
Thank you very much.